students, good morning to all of you. Uh, we were discussing the chapter wave optics. In the previous class, we gave an introductions of the wave optics chapter, and today we're going to discuss about Huygens principles of wave optics. The before going to discuss about Huygens principles of wave optics, we'll discuss a simple topic that we should know, that is the wavefront. So we'll discuss what is wavefront first. You please note down wavefront. So if we discuss about wavefront, and if you want to write the definitions of wavefront, the definitions of wavefront will be, you please write down the definitions of wavefront. It is continuous. It is continuous locus. It is continuous locus of all the particles. Of all the particles in the medium. Okay, it is continuous locus of all the particles in the medium. In the medium that vibrates in same phase. Vibrate in same phase at an instant. This is the definitions of wavefront. You kindly note it down. It is continuous locus of all the particles of the medium, not in the medium, of the medium. Particles of the medium that vibrates in same phase at an instant. That means locus of all the particle means in a system we know there are so many particles. A system contains millions of particles. That means when they will form a locus, and after forming the locus, when they will form locus, they will be vibrating in the same phase. That means the phase of vibration of this particle will be similar. If I go to make you understand by the help of a definition, diagram, so it will be like that. So let us consider a very simple example for it. That is, if I consider that this is a source of vibration. Source of vibration means, remember we're studying the Huygens principle. What did Huygens told us in his opinion? Huygens told that the light particles travels in the form of wave. We have discussed in the previous class that light travels in the form of wave. That means if you consider this is the source of disturbance, that is at the very first the particles will be disturbed fast. That means at the very beginning, if you consider a source of light, then what will happen? Very beginning, at the first, the particle will get disturbed. Once the particle will get disturbed, it will start vibrating. Again, it will reach to another point, and this particular point will disturb that point, and that point will again start vibrating, and like that, some wave will form. This is generally called wavefront. The basic example you can consider that if you go to a pond full of water, and if you throw a stone at the middle of it, you can see that water starts vibrating. These are a wavefront in case of light. We can understand by taking that an example. So if you consider that this is the source of a disturbance, and let us suppose this is O, and instant, that is time, suppose here when time is equal to 0, Right now time is 0 I have considered, and this is the source of disturbance. That means now this part, in this point the particle will get disturbed now. So if I consider that in this medium the speed of light is c. C is the what? Speed of light we have considered. So if we want to know that after t is equal to t time, or after t time, what will be the positions of these particles, then we can find out the positions of the particle after t time by multiplying c and t. Am I clear? Since velocity is equal to distance upon time, so distance is equal to velocity into time, or speed into time. So if we multiply c into and t, that means after t time. So if I consider that this much is the distance, if I consider this is the position of this particle after getting disturbed at t time, that means when t was 0, this was the position, and after t time this particle has arrived in this point. How many distance it has traveled? We can easily find out that it has traveled ct amount of distance. Is that clear? This is point of disturbance. I have already told you that in a system or in the medium there are so many particles, and once they got disturbed they start moving. And if you consider in case of light, according to Huygens, they move in the form of wave, so that they will go down in the form of wave. How many distance they are traveling? This is called ct distance. We have found how we have found that this is, we have multiplied speed into time, hence we have got the adequate distance traveled by this particular point. Now if we consider that this disturbance has got 3-dimensional, so if we get the 3-dimensional, then what will happen, that if we consider, suppose this way, suppose after t time it is a p point. Am I clear? And if you consider so many points, that means this is suppose p, this point is p1, and how can you come to know that this point will be at p1 distance? Since at the very beginning we considered that this point after t time will be in this point and it will travel ct distance. It's very simple. Now we'll consider again same radius ct from here, ct from here, ct from here. Now if you consider this much of radius ct, then this will be the p1 point. Again if I consider this is suppose p2 point, again we have considered how much distance ct, that means ct distance we have considered, and that is how we can find out this will. So this is suppose p3, and like that this is suppose your p4, and like that it will continue. Remember, all the distances from this point is p up to p1 is ct. That means we have assumed that up to this point again ct, up to this point again ct, up to this point again ct. That means now if we simply join all the point by a curved line, then this will be the wavefront. Am I clear? This is going to be the wavefront. So it's very simple. Now this is going to be your wavefront. Okay, so this is the wavefront. So what happening in this case, that it is the continuous locus of all the particles. As you can see that all this particle p1, p2, p3, p4, like that, they are forming a locus, they are forming a continuous locus. Am I clear? This is a continuous locus formed by this particle. How they are forming? They are vibrating. That means once they starting from this source of disturbance, each and every point are vibrating from the center. Am I clear? They are vibrating in the same phase at an instant. This is called a wavefront. Am I clear? So wavefront is nothing but wavefront is a continuous locus of all the particles of a medium which vibrates in the same phase at an instant. So this is how we can find an wavefront. So this is a wavefront. If you consider if you consider some more points, suppose this is p5, again this distance will be equal to this CT. Again we'll go here this point. If you consider P6, again it will be CT. Okay, like that we'll find a wavefront. That is how a wavefront is produced. Now if you consider for a wave now, if you go to take another example of it. So if you consider, suppose this is the point object, point source. Now suppose if you directly consider these are a wave in different direction. Okay, these are the wave, and they're traveling in different dimension. If you see in this diagram, I want to tell you clearly. So what is this? This is one phase. These are the phase. These are the phase of the wave. These are the phase of the wave. That means this is the crest. This is the crest. This is the crest. This is the crest. This is the crest of this wave. So as per the definition is concerned, that they vibrate in the same phase. That means this is going to be your one wavefront. Am I clear? So if I write it in bigger scenario, that means if I consider, suppose from this source of disturbance, these are the wave. Okay, these are the wave. They're moving in different dimensions, shape, like that. Now if you consider in this wave, this is the crest, this is the crest, this is the crest, and this is the crest. This is the crest. That means this is a phase. This is the phase of this wave. So if I join them by a curved line, so this is going to be a wave. Again, if you go to the next, suppose this is a crest, these are crest, these are crest, these are trough. So if you go to join them, similarly, they're going to be a wavefront. These are wavefront. Am I clear? And like that, so many wavefront can be produced by this process. Am I clear? Remember that the particles vibrate in the same phase at an instant. That means their phase should be same. So this is a wavefront. This is a wavefront, and this wavefront will be known as primary wavefront. Am I clear? This will be known as primary wavefront. These are secondary wavefront or wavelets. Am I clear? So these are known as, this will be known as secondary wavefront or wavelets. They will be known as. So this is how a wavefront is produced. This is the better diagram to understand than the previous one I have given you. Okay, so again I am telling you the what is wavefront. Wavefront is the continuous locus. These are locus, continuous locus. Okay, continuous locus formed by all the particles. Continuous locus of all the particles which vibrates in the same medium, the same phase at an instance. I hope you have cleared it. Better example you can find that in case of a pond full of water, if you drop a stone, that you can find so many waves of water. If you consider, same thing you can bring in the concept of the light also. Am I clear? So this is your wavefront. Now let us come to the types of wavefront now. Types of wavefront. You can write the types of wavefront. Types of wavefront. How many types of wavefront generally we have? We have spherical wavefront. Okay, then we have cylindrical wavefront, and finally we will have plane wavefront. We can have three types of wavefront. You please noted down. Spherical wavefront, cylindrical wavefront, and plane wavefront. Like that, we can get three types of wavefront. Now, how these wavefronts are produced? How can we get a spherical wavefront? How can we get a cylindrical wavefront? Or how can we get a plane wavefront? We will discuss now. You first write spherical wavefront. If we discuss first about spherical wavefront. Spherical wavefront. Now spherical wavefront, you write first that spherical wavefront is produced for a point source. Okay, it is produced due to a point source. It is produced due to a point source. Okay, so we can find spherical wavefront that is produced for a point source. So if we consider this is a point source, suppose it is somewhere, it is a point source. Okay, if you consider it is a point source, so if you consider that these are some wave like that, if you consider the wavefront of for this point source will be produced like that, these are a wavefront like that, these are a wavefront. That means for a point source, the wavefront produced is always spherical. So this is a spherical wavefront term. This is spherical wavefront and it is producing for a point source. For a point source, what wavefront is produced? That is your spherical wavefront. Is that clear? And in this case, the intensity of wavefront will be inversely proportional to square of the distance. That means as the distance of the wavefront will increase, intensity will decreasing. Amplitude of wavefront will be inversely proportional to the distance. So these are the two conditions you should remember. In case of a spherical wavefront is produced due to a point source, and its speciality or specification, if we discussed, that the intensity will be inversely proportional to square of its distance, and amplitude will be inversely proportional to the distance. Okay, so this is all about spherical wavefront. Or if I take one more diagram, by one diagram also you can see, if I consider, suppose if you find some difficulty in this diagram, let us suppose this is a wave, same thing only, and this is the same phase. Now this is going to be the wavefront, these are going to be the wavefront. Remember, all these wavefront are producing because of point source, so these are also spherical wavefront. So these two diagrams are similar, but I have just made it distinctly so that you have no problem in understanding. Next we will go to the cylindrical wavefront. Cylindrical wavefront. Number 2. Cylindrical wavefront. As we found that the spherical wavefront is produced due to a point source. Now this is produced due to a linear source. This is produced due to a linear source. Cylindrical wavefront is produced due to a linear source of particles. So what is linear source of particles? So if I consider this is the linear source, and if you consider that for this point, for all this point, there will be some wavefront, and if for this point, this is the wavefront, you can easily get it, okay? Because this will behave like a point object, okay? Similarly, in this case also, like that, we'll find so many spherical wavefront in this series, okay? Now finally, if I join them, if I join them, I'll find a spherical wave, a cylindrical wavefront like that. This is going to be a cylindrical wavefront, and this cylindrical wavefront has been found because of a linear source. This is linear source. This is linear source, and this is your cylindrical wavefront. This is a cylindrical wavefront. Am I clear? Have you understood it? So cylindrical wavefront is generally for linear source, and similarly intensity of a cylindrical wavefront I. Okay, intensity of it is going to be inversely proportional to the distance r, and amplitude is going to be inversely proportional to square root of the distance. These things you remember. This is for a cylindrical wavefront. Cylindrical wavefront is produced because of linear source of object. Okay. Now next is the plane wavefront. Plane wavefront is, you can write, plane wavefront is a small part of both cylindrical and spherical wavefront. Remember, plane wavefront. So plane wavefront, as you can write, it is the part of both spherical. It is the part of both spherical and cylindrical wavefront. Am I clear? It is a part of both cylindrical and spherical wavefront. So if I draw a diagram for it, it will be like that. These are the plane wavefront. Okay, these are the plane wavefront. Plane wavefront stands like that. And interestingly, the intensity of this type of wavefront does not dependable on the distance, and similarly amplitude also not dependable on the distance. Those things you should remember nicely. So this was all about the types of wavefront and definitions of wavefront. Okay, and one more property of wavefront is that the rays of light is always perpendicular with respect to the wavefront. Am I clear? So if we consider in case of, suppose it is a point source, and for this a spherical wavefront is produced. This is a point source and this is a spherical wavefront. So if we consider these some radial line like that, these are the rays of light, and these rays of light are always perpendicular to the wavefront. These things you remember, that rays of light are always perpendicular with respect to the wavefront. Is that clear? So this was all about wavefront. I think you have understood. It's a very important thing in order to go to the Huygens principle. So in case of the example of wavefront, I have given so many diagram. You just practice it nicely. The next class we will come back with the Huygens principle of secondary wavelengths. Thank you.